Hello everyone. This lesson will conclude the remainder of chapter 3. As we've discussed in previous lessons, we will start with the objectives and the goals for this particular lecture, and it will be able to sketch a vector direction and a plane within a unit cell when given 3 or 4 direction index integers. So basically, if we're given some indices, how can you sketch a vector direction or a plane? The second part will be to be able to specify these indices based on a given vector direction or plane. So if you're given a sketch, how do you specify the indices? And finally, one other objective will be to calculate linear and planar atomic densities. So just to give you a brief overview, in the previous lesson, we talked about atomic packing factors, and those were related to the volume of the unit cell. And in this case, we'll be looking at linear atomic densities, which are based on distance packing factors, and planar atomic densities, which are based on areal packing factors. So you can look at the fact that we're looking at a line, a plane, or a volume, and there's a way to relate the number of atoms in each of those different directions to some kind of packing factor. So those will be our 3 main objectives for the lesson today. So we'll first of all begin with crystallographic systems and points. Basically, how do we numerically describe points or positions within the unit cell? So as a brief review, we talked about the definition of a unit cell as the building block of a crystal structure, and then the lattice as the 3-dimensional arrangement of points representing the atomic centers. So we talked about the unit cell and then the lattice being points that are overlaid on that unit cell. And we started by talking about the 7 different crystal systems that we have, and these are all based on some relationship between the edge and then the angles between those edges. So for instance, in a monoclinic crystal system, we have 3 different sides which are of different lengths, and then we have 2 angles that are the same and a third angle which is different and either greater than or less than 90 degrees. And so you have 2 angles that are 90 degrees, so in essence 2 of those sides are perpendicular to each other, and then a third side is not perpendicular. And then when we overlay the lattice points on those crystal systems, we end up going from a 7 crystal system to a 14 crystal lattice system. And the main difference being where the lattice points were located. And so these were divided into 4 different kinds. We have a simple or primitive, where you have your lattice points at the edge of each of your unit cells. Or then you have a body-centered, where you have the lattice points at the corners, but also within the body of the unit cell. And then you have a face-centered, where you have them in each face, and then you have an end-centered, where you have them basically on either end of your crystal structure. So based on those prior concepts that we've defined, we now want to look at numerically describing these crystal systems. So the first thing we'll talk about is a coordinate system, which is, as you've done in pre-calc and calculus, you can have the x and the y-axis, or the x, y, and z-axis. In this case, because we're doing 3 dimensions, typically your coordinate system will be the x, y, and z, although it will not always be Cartesian, in the sense that you may have more than 3 axes, and this applies to the hexagonal system, which we'll cover later on. The other thing we will talk about when describing crystal systems are the lattice constants. And so your lattice constants describe the edges of or the dimensions rather, of your unit cell. And you'll notice that those constants are also parallel or related to the axis that you choose. So for instance, the C lattice constant is related to the Z axis, and so on and so forth. Now, once we've described a coordinate system, it helps to now be able to define points within the system. So for instance, the origin, which is typically our point of reference, is where your x, y, and z axis coincide, and that corresponds to a point that is 0, 0, 0. On the other hand, the 1, 1, 1 coordinate is one where we moved one unit along the x-axis, 1 unit along the y-axis, and 1 unit along the z-axis to get the 111 point coordinates. Now, if we look at the crystal system that we described previously, which would be the body-centered cubic, you will notice that this 0.5 here is located exactly at the center. So it's when we've moved, basically from the origin, moved half in the x direction, half in the y direction, and half in the z direction. All of these were positive, and so we end up with a coordinate system that is a over 2, b over 2, and c over 2. So again, we're relating our coordinate system to the lattice constants of our unit cell, and we end up with the coordinate system that's 1/2, 1/2, 1/2. The other thing to note is that a translation of a point is basically another point in a similar unit cell. So for instance, if I look at this point, which is defined by this unit cell right here, if I translate this by 1 times b, I'll move 1 in the y direction, but I would exactly have that same point again in the adjacent unit cell. What if I translate by twice the c distance? I will again move 1c and 2c, and I end up with a point that is in another unit cell, but it's the same exact point. So the conclusion here really is that if I take an integer multiple of any of my lattice constants, I will end up with an identical position. And this applies to whether I use positive integers or negative integers. So the next part, which we'll discuss, are your crystallographic directions. So we'll start with the point coordinates, and I want to relate those point coordinates to directions. And these directions are defined by a term known as a vector, which describes a line and a direction between 2 points. And so the way we typically describe this is that, let's say we have our unit cell located here. So the first thing we do, again, we have our x, y, and z axis as previously discussed. So the first thing we'll do is look to see if we need to reposition the origin to be at the tail of the vector. And if you look at this green vector right here, this green line, which is an arrow, we start at this point and end at this point. And this point where the tail of the vector is at the origin, because again, it's the point where our x, y, and z axis meets, and so we do not need to reposition. Then the next thing we need to do is to read off the vector projections in terms of the unit cell dimensions a, b, and c. So we move, so if we look at this, we can see that this vector right here is projected along the x-axis, and it takes the full length of this dimension. So we'll describe that as 1a. And then we see that the vector does not move in the y direction, so there's no distance to consider in the y direction. And then it moves halfway in the z direction, and we'll call that 1/2 c. So we end up with 3 points, or rather 3 coordinates, which are 1, 0, and 1/2 for the x, y, and z axes respectively. Then the next step is to simplify this to obtain the smallest integer values. So we are either going to divide by a number to reduce the lowest common denominator, or we're going to multiply by a number. So in this case, because we have a fraction, we can multiply all of these by 2, and we end up with coordinates of 2, 0, and 1 for the x, y, and z axes respectively. And finally, we can enclose these values in square brackets, and that will give us the crystallographic direction depicted in this picture, which is a 2, 0, 1. And again, we always enclose those in square brackets. We can do the same for this crystallographic direction shown here. So again, we need to look at whether we need to reposition the vector for the tail to pass through the origin, which we notice that we don't have to, because again, the tail of this vector is at the origin. So then again, we read off the vector projections in terms of the unit cell. So we go back 1, and because we're going in the negative x direction, that's a negative 1a. And then we go to the right, so that's plus 1b. And then we go up, that's plus 1c. So we end up with our coordinate system of negative 1, 1, and 1, which again describes this crystallographic direction based on how we moved from this origin to the head of the vector. And so we see if we need to simplify that. We don't, because all of these numbers are 1, and therefore we enclose them finally in square brackets. And so anytime you have a negative value, you would put that as an overbar. So the overbar here represents a negative index. So our Miller indices, or our indices for this particular vector, is overbar 1, 1, and 1. And so if you go back to the VMSC site, which I provided in the very first lesson, you can see some other examples, and you'll be able to visualize some of these vectors. And so this is an example here, which is representative of the 1, 0 overbar 1. So this vector here represents this particular Miller index direction. And with that being said, we're going to do some examples. So this will be a good place for you to pause this video and then try to work out some of these examples on your own. So I'll first of all start with vector C, so you can pause and try to see if you can find the direction of vector C before I show you how to do it. Okay, so the first step is, if we look at this vector, we need to reposition the origin. So our origin is typically here, and we need to reposition the origin so it is at the tail of this vector. So that's what we'll do first. And we'll place the origin at the base. So now this here represents our origin. And then we need to find our projections in the X, Y, and Z direction. So in the X direction, we move forward 1/2. And then we move to the right 1/2. And then we move up 1/2. So all of these directions represent positive directions for all of these directions represent positive directions, and so we'll end up with 1/2 A, 1/2 B, and 1C. And we take off the letters, and we end up with 1/2, 1/2, and 1. And again, the next step here is to simplify. So we simplify by multiplying through by 2 to get all integers. And so we end up with 1, 1, and 2, and we finally place that in a bracket, which gives us 1, 1, 2 as shown. And so for vector C, we end up with this 1, 1, 2 Miller index. All right. The next one we'll do is vector B. Again, at this point, I will encourage you to pause the video and try to calculate or figure out what this crystallographic direction is based on what we did for vector C and based on the methodology we've discussed. Okay, so this is how we'll solve this. So we have vector B, and again, the tail is not at the origin, so we move the origin to the tail of B. And now we're going to find the projections. So again, what is a projection in the X direction? So now we're going back into the screen, or going back into the page. So that's a negative 1, because we go all the way back across from one edge of the unit cell to the other. And then we find out what's happening in the Y direction, which again is to the right, so it's in the positive Y direction. And then we notice that we don't move up or down, so we've covered everything we need to cover, so it's 0 for that direction. And so we end up with these projections, which are negative A, positive B over 2, and 0C. We remove the letters, we end up with negative 1, 1/2, and 0. And then we simplify, and we have negative 2, 1, and 0. And finally, we put them in square brackets. So we have overbar 2, 1, 0. And that represents the crystallographic direction for vector B. So there's other examples in the textbooks that I've recommended, so try to do some of those and then ask me questions if you're struggling. So the next thing we'll talk about is the concept of linear density, which I explained to be basically the atomic packing factor for a line. Okay, so the linear density is given by the number of atoms centered on the vector divided by the unit length of that direction vector. So we're going to do an example, which is what is the linear density of aluminum in the 1, 1, 0 direction, given that A equals 0.405. So aluminum has a face-centered cubic unit cell, and this is the dimension of the edge, and we're given this 110 vector, and we have these atoms X, Y, and Z. And so we're going to find the linear density of this vector. So keep in mind that linear density here has to do with a distance or a line. So it's not an area, it's not a volume, it's a line. So if we're going to find because we need to find the length of this direction vector, if we're going to find this length, we need to relate it to the components of the unit cell. So this diagonal is going to be related to this side, which is A, and this side, which is also A as well. So if we look at this from the top, we end up with this projection where we have X, Y, and Z atoms, and then we have our two sides, A and A. So we have A here, and this is the length of our direction vector. And based on Pythagoras, the vector length, which is this, is going to be based on, the vector length squared is based on the square root rather of a squared plus a squared, and we end up with square root of 2 times a. So this here gives us the bottom of this, which is the unit length of the direction vector. And then the next part is to figure out what the number of atoms centered on the vector are. So remember I said, so in the previous part we've talked about how like corner atoms are 1/8. But in this case, we're not looking at the volume of the unit cell. We're not looking at the volume of the unit cell. We're looking at this particular distance, because we have X, Y, and Z atoms are all centered on this vector, and this vector completely goes through the Y and then goes only through half of X and half of Z. So therefore we have two atoms where one of Y, half of X, and half of Z. And so that gives us 2, which ends up giving us the numerator on this linear density formula. So we end up with a value that's 2 divided by square root of 2a. We plug in the value of a, and we end up with 3.5 nanometers, 3.5 per nanometer. So that gives us the formula on how to calculate the linear density. So as I mentioned in the beginning, sometimes you'll be dealing with a hexagonal crystallographic direction. So the cubic crystallographic directions typically have 3 axes, while the hexagonal crystallographic directions will have 4 axes. And so one way to do this would be to follow the same methodology that we followed for a cubic unit cell, where we start by repositioning the vector to pass through the origin, and then we read out the projections based on the axes that were given. So A1, A2, and Z, which are related to the lattice parameters or the lattice constants for the hexagonal cell, which are A and C. So we find the projection of the vector in terms of A and C. Then again, we adjust. So in the cubic unit cell, we did it for X for A, B, and C. And for the hexagon, we'll do it for A and C. Then in step 3, we adjust to the smallest integer values by either multiplying or dividing. And then we enclose our answers in square brackets, and we give those terms U prime, V prime, and W prime. And then once we have those, we now find our 4 axes based on these formulas shown, where U is based on the combination of U prime and V, V is based on V prime and U, T is based on U and V, and then W is based on W prime. And once we have each of those values, we put them in square brackets, which will now have, instead of a 3-index direction, we have a 4-index direction. And that will define our hexagonal crystallographic directions. So to show you how this works, we're going to do an example. And we'll be working with this vector in green shown here. So again, step 1. Reposition the vector so that the tail passes through the origin. We don't need to do that here because the tail of this vector passes through the origin. The next step is to look at the projections. So we have this projection here, which is for the A1, and that goes for a full length of A, as seen by this, and then A2 which goes a full length of A as well, as seen by this direction. And then we don't go up or down, so that's 0C. The next step is to reduce the values if we need to, which we don't. And then we put those in parentheses. So that represents our first 3 index, which is the first step we need to obtain. The next step is to convert these 3 indices into 4-axis parameters using the formulas in the previous slide. So we convert our u prime, v prime, and w into u, v, t, and w, and we end up with 4 different coordinates. And once we have those 4 coordinates, we reduce them. So in this case, we're going to multiply by 3 to get only integer numbers. And we have 1, 1, -2, and 0. And then we place those into square brackets. And finally, we have our 4 Miller indices. So again, for the hexagonal closed pack, because of the fact that we don't have our traditional X, Y, and Z axis, but we have what we call A1, A2, A3, and Z axis. We can translate our 3 Miller indices shown right here into 4 Miller indices. Now, just as we've been able to determine our vector, we've been able to look at our vectors and obtain the numerical description of them. Sometimes you'll be required to look at a vector, or look at a Miller index rather, and use that to sketch a vector. So you can go from either sketching a vector, given a sketched vector, and finding the indices, or given the indices, find the sketch. And so we sort of go backwards in that case. So in this case, we would, once you're given the Miller indices, you remove the brackets, then you divide by the largest integer, so all your values are less than or equal to 1. You multiply the terms by the appropriate unit cell dimension, and then we construct the vector by stepping off these projections. So, if we go 1 in A1 or 2 in A2 and so on and so forth. And so we're going to do an example to actually predict how to describe this. So in the next example, we're given this direction, which is over bar 1, over bar 2, 1, 3. And so those are our our Miller indices, and we need to take those numbers and then try to draw them. Okay, so in this case, rather than the A1, A2, and Z that were given before, now we have the 4 axes, which are A1, A2, A3, and Z, and each of these letters account for each of those axes. So remove our brackets, and then we place the numbers under the respective axes, so -1, -2, 1, and 3. The next step will be to simplify, and we simplify by dividing by 3, with 3 because 3 ends up being the largest number here, so all our numbers have to be, as I said in the previous slide, they have to be less than or equal to 1, so we're going to divide by 3. And then the next step is to look at those projections. So that's -a/3 for the A1 axis, -2a/3 for the A2 axis, a/3 for the A3 axis, and c for the Z axis. So keep in mind that the A here represents the sides of this hexagon. Hexagon has 6 equal sides, so that's the A. And then C here represents the heights of that prism. So the next thing we're going to do is construct a vector. So step 1, we start at the origin, as we've talked about before. We're going to proceed -a/3 units along the A1. So this is the positive A1, and because that's negative, we go back -1/3. And then we go -2a/3 for the A2 axis, continuing from that point. So the A2 axis, positive goes in that direction, so our negative is going to be in the opposite direction. But we don't start from the origin, we start from where we ended, so we move backwards that way. And then the next one is 1/3 units parallel to the A3, so we move 1/3 that way, and then we go C units parallel to the Z axis. So C units parallel to the Z axis to point S. So we start from here and go all the way to that point, and that's how we end up with this vector, which starts its tail starts at the origin and its head goes all the way to the final projection that we did. So this direction, the 1, 2, 1, 3 direction in a hexagonal unit cell, is given by this green vector. So once again, I'll encourage you to do some examples from the book to be able to understand this concept. So practice, 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 because the thing about visualization is that sometimes it takes a little bit of time to see what's going on. So in the previous slides, we talked about distances and vectors. So all our information was based on one dimension. And in this case, we're going to be talking about planes, which are two-dimensional representations within a unit cell. And this can also be described by 3 or 4 indices based on whether we're doing a cubic unit cell or a hexagonal unit cell. So just like the vectors are represented by indices, our crystallographic planes are represented by Miller indices. Now, the indices are basically reciprocals of the intercepts of the axis. So once we figure out where where the plane intersects the axis, we take the reciprocal of that and we do some reduction, and we end up with these numbers that describe the plane. So you can see some examples here, which are this shows an example of a 0, 0, 1 plane. This shows examples of 1, 1, 0 plane, and this shows examples of 1, 1, 1 planes. And one thing to always note is that if you have two planes that are parallel to each other, they're equivalent and have identical indices. So even though so for instance, you have a 1, 1, 1 here, even if you have a 2, 2, 2, it will still be the same plane. It's just very slightly different in its notation. So in finding the Miller indices for a plane, we will follow a certain type of methodology. So let's look at this example where we have our cubic unit cell and we have this blue plane shown here. So the first step is to determine if the plane passes through the origin. And if it does, we either construct a parallel plane or we create a new origin. So in this case, because the origin is at this point where the laser is pointing to, we don't have to do anything because this plane does not intersect that particular origin. Then we read off the intercepts of the plane with axis in terms of A, B, C. So in this example, we have our ABC, and then we're going to read out the intercepts. So for instance, this particular plane crosses the x-axis at 1 when the value of A is 1. It crosses the y-axis where the value of B is also 1. But if we look at this plane, it does not cross the c-axis at all. In fact, if this plane were extended upwards, we will say that that plane never is impossible to cross the c-axis. So we'll say that it never crosses, and so it's an infinite separation. And so our intercepts for our x, y, and z, which represent our lattice constants A, B, and C, are 1, 1, and infinity. So right now we've completed step 1 and we've completed step 2. So once we have these intercepts, the next step is to take the reciprocal of the intercepts. So 1 over 1, 1 over 1, and 1 over infinity, and that gives us 1, 1, and 0 because 1 over infinity is 0. And then we reduce those to the smallest integers either by multiplying or dividing. In this case, we don't need to do anything because we have 1, 1, and 0. And the final step is to enclose those in parentheses. So for this particular plane, our Miller indices are 1, 1, and 0. Let's do another example. So now we have a different plane, which is, in the previous one, we had a square plane. In this case, we're going to be dealing with a triangular plane. And the steps are still the same. So, once again, do we need to reposition the origin? No, we do not, because this plane that we're dealing with does not cross the origin. So the next thing to do is to read off the intercepts. So this triangle appears to, we're just estimating based on visualization, that this triangle right here crosses the x-axis about halfway through this unit cell dimension. This is about half A. And then for in the y direction, it crosses the y-axis at the full length of B, and then it crosses the c-axis at about, let's say, 2/3 or 3/4 of C. So we look at our intercepts as 1/2, 1, and 3/4. Again, notice that all of these values are positive, and that's because all of these points where they cross the axis are positive with respect to the origin. So positive x, positive y, and positive z. So now we have our intercepts. The next thing to do is to take the reciprocal of those intercepts. So 1 over 1/2 and so on and so forth. And once we have that, our values become 2, 1, and 4/3. And now we have to reduce to the smallest integer. So rather than dividing, because we have this fraction here, we're going to multiply every single number by 3. When we do that, we get the values of 6, 3, and 4, and our Miller indices are 6, 3, 4 in parentheses. Now, what if we're dealing with a hexagon? So now we have this hexagonal plane. We have this hexagonal unit cell, and we have this plane inside that unit cell. And we have our A1, A2, and A3 axis, and our Z axis as well. Again, all of these are with respect to A and C. We'll use the same methodology. We stake out our table, which is going to be A1, A2, A3, and C, and then we describe where this plane that we're given crosses each of those axes. So if we look at this corner here crosses A1 at the full length of A, and it crosses A1 where it crosses in the positive direction of A1. So we'll call that our positive 1. And then we have the A2 axis right here, but we have this plane crossing at this point. So this is the positive A2 direction. So this particular plane crosses A2 at the negative A direction. Okay, so again, this is negative A. We're going from the center to the edge, so this is negative A. So we'll say that for the A2, it crosses in negative A direction. And then this is our A3 axis. But if we look at our plane, this plane never crosses A3. And because it never crosses A3, the respective index or the respective value for that would be infinity. While for the Z-axis, this plane crosses at this maximum length, which is the full length of C. So we end up with 4 numbers, which are 1, -1, infinity, and 1. And then second step, we take the reciprocal of each of these numbers, which gives us 1, -1, 0, and 1. Do we need to reduce? No, we do not. We take our Miller indices, and that will be 1 over bar 1, 0, and 1. So again, the methodology that we use in the cubic unit cell is very similar to the one that we use for the hexagonal, except we have one additional index to worry about, but the steps are still the same. So with that being said, we'll do some examples. So in this first example, I'm going to show you how to sketch a plane given the Miller indices for that plane. So the first thing we'll do is sketch our cubic unit cell. Again, it's very important that you're able to do this on paper, okay? Because one of the critical things that I mentioned to you, one of the objectives is for you to be able to sketch a unit cell. So it's important for you to be able to at least draw the unit cell, look at where the origin is, and look at where your positive x, your positive y, and your positive z is. So we start with our Miller indices, which are 1 over bar 2 and over bar 2. We remove our brackets. We have 1, -2, and -2 for our A, B, and C. Do we need to reduce? It's not necessary to reduce here. So we keep those numbers. And then the next step is to take our reciprocals. So our reciprocals give us 1, -1/2, and -1/2. So now we're going to mark out those intercepts on the unit cell that we've drawn. So we start by marking the origin, and the origin is shown there. And then we deal with the intercept for the positive x-axis, or for the x-axis rather, which is 1a. And we notice that that goes the full length of the unit cell because it's the full length of the a lattice constant. The next intercept is -1/2, right? So we have our positive y here, so we show that direction, which is in the negative y direction, and it's halfway. So this distance is the full length of b. We choose half of b. And then the next index is the -1/2 for c. So again, that's the negative z direction, and we go half a length. And so these represent our 3 points, and finally we join all those 3 points, and that gives us the plane that we're referring to. So that plane, the yellow triangle shown here, is the 1/2/2 plane, okay, within the cubic unit cell. All right, so the next example we'll do is for a plane that passes through the origin. As mentioned, when we're trying to find these Miller indices, the first step is to figure out whether we need to reposition the origin or not. In the previous examples that we've seen, that wasn't an issue, but when you have a plane, for instance, a plane here that passes through the origin, we need to do something. So the first step is to reposition the origin. So all we simply do is move the origin from this point where it typically is to this edge of the unit cell. The reason why we're moving it to that edge is because we still want we want to use the point that is closest to the plane we're interested in. So while we could have used this point, or this point, or this point, or this, or this, or this point is the one that's closest to that plane, and that's the one that we choose. So now that we have that, the next step is to look at the points where we cross the x, y, and z axis. So we cross the x-axis at this positive 2/3 position. We cross the y-axis at this, if this is the origin, we're crossing the y-axis at the negative 1b position. And then we're crossing the z-axis at the positive 1/2 position. So our intercepts are 2/3, -1, and positive 1/2. And that gives us the values. And then the next thing we do is, again, we're going backwards, so we're going to take the reciprocal of those numbers. And once we take the reciprocals, we end up with these values: 3/2, -1, and 2. And then we reduce to get all integers. To do that, we multiply everything by 2, and we end up with 3, -2, and 4. And finally, we put those in parentheses, which are 3/2 and 4. So remember, Miller indices for planes are parentheses. The crystallographic directions are in square brackets. Okay. All right. So this is the point where we do another example, which again we're dealing with plane A. This is where I would encourage you to pause the video and try to figure out this problem on your own before I show you how to do it. So pause the video and try to do the work. Okay. So we have our index, our plane here, and typically our origin is in this position where the x, y, and z axis meet. So the first step again is to see if we need to reposition the origin. Now we want the origin to be as close to the plane we're interested in as possible, because this is where the A plane is, rather than having the origin at this point. We'll move the origin to this point, which is the point that's closest to A. The way you can think about this is that we want the vector itself we want the plane to kind of enclose the origin. So if you think about this triangle being shown, if I was going to move this triangle to cover up the origin, that point will be the one that this plane will cover up. And so again, you can think of it in two ways: either the origin being the point closest to your plane, or the one that's basically consumed or covered up by your plane. Okay. All right, so we position our origin over here, and then we mark off our points relative to the origin. So we have this point, which is positive 1/3, we have this point, which is positive 1/2, and we have this point, which is negative 1/2. So our intercepts are 1/3, 1/2, and negative 1/2. The next step is to take the reciprocal, which gives us 3, 2, and negative 2. And then we see if we need to reduce, which we don't. And finally, we enclose those in parentheses. And so we get 3, 2, and over bar 2. And so those will be the Miller indices for this particular plane. At this point, again, I will encourage you to do as many examples as possible because visualization can be tricky. Okay, so the next thing we'll talk about is the planar density. So when we talked about vectors, we talked about linear density. For planes, we're going to be talking about plane density. So again, the planar density here, the number of atoms centered on a plane divided by the area of the plane. And so as an example, we're going to figure out the planar density of the 1, 0, 0 plane for iron, where the atomic radius for iron is 0.1241. So iron has a body-centered cubic unit cell. I do not expect you to memorize this. This is just will be provided to you. So in this case, and this is something you can look up in the book basically. So iron has a body-centered unit cell, and the 1, 0, 0 plane is this square shown here. So if we do a projection of that and we just zoom out of our unit cell, we will see that our 1, 0, 0 plane is this series of lattice points, which are look like a bunch of squares basically. Okay, so if we take one of those squares, our repeating unit is these 4 atoms with the square direction shown below. So keep in mind we're trying to find both the number of atoms centered on the plane and then the area of the plane as well. So if we're looking at the area of the plane, is going to be basically this is a square, and so we're going to find one of the sides and square that side. So our side A is given by 4 square root of 3 over 3r. So if you just go back and look at the relationship between the edge of a body-centered cubic unit cell and the radius, this is the formula that we worked out previously. And so now we're going to, the question then becomes, before we go to that, how many atoms are centered on this plane? So if we look at this, we have a quarter of an area, a quarter of an area, a quarter of an area, and another quarter of an area. All of that adds up to one full area. So we'll say we have 1 atom fully centered on this plane. Again, in the previous one, we talked about distance. In this particular one, we're talking about area. So this is not 1/8 of your atom like we've talked about before, but this is 1/4 of your area. Okay? And so with that in mind, we have 1 atom centered on the plane, and the area of our plane is a squared. We plug in this relationship with r for a squared. We end up with 12.1 atoms per nanometer squared, and we can convert from nanometer squared to meter squared, and we end up with 1.2 times 10 to the 19th atoms per meter squared. So this would be the planar density for a 100 crystallographic, for the 100 crystallographic plane of iron. What if we did the planar density of the 111 crystallographic plane? We can start again with our visualization. So we have the same body-centered cubic unit cell, but your 111 plane is a triangular plane, which is given by that below, where the sides of your triangle are basically the diagonals of the faces. And so when we zoom out, we have this, all of these show the 111 plane, and then we end up with this triangle. Okay, and so for this triangle, each side is given by the square root of 2a, based on the fact that we have this diagonal, which is related to this side A and this side A. Okay, and then going back to what we have for a excuse me, going back to what we have for a body-centered cubic, your A is given by 4 square root of 3 over 3r. All right, and then we look at each of these atoms and we're trying to figure out how much of this atom is within this unit cell. Each of these sides are equal, right? So that means each of these angles are 60 degrees. You take them all together, that gives you 180. That gives us half an atom, okay? So we have half an atom, so that gives us the top part of this, the numerator for our fraction. Now we need to figure out the area of the plane. So the plane we're dealing with is a triangle, and the area of a triangle is 1/2 base times height. So now that means we have to figure out the height of this triangle, which looks like this. So we have this relationship between the height, half of the base, and the edge. So we go back to our favorite equation, Pythagoras, which is that h squared plus 1/2 the base squared equals the side squared. We work that out, we get that h squared equals 3a squared over 2. We take the square root of both sides, we get that h is equal to the square root of 3 over 2a. So now we have the height, and we know what the base is. So the area is 1/2 base times height. We plug in the base, which is the distance from here to here, which is the edge, or rather this diagonal that we've discussed. And then we multiply that, we get this formula. We plug in the value for A, we get this expression, and now we have the area of the plane in terms of R, and we know that there's half an atom. So our planar density is given by 1/2 divided by A squared of 3 over 3, which gives us this final value, 7.03 atoms per nanometer squared. So that would be how you calculate the planar density for a 1-1-1 body-centered. But on the exam, for instance, on a quiz, you could be asked about the planar density of a 101 plane for a face-centered and so on and so forth. So again, this is where it's important for you to do quite a bit of practice. So why is this relevant? Okay, so we talked about how the atomic packing factor, when we talked about the volume of the unit cell, was related to the mass density. For linear and planar densities, those are relevant to characteristics when we're considering slip in metals. And slip is related to plastic deformation of metals. We're going to cover that in chapter 8. But basically, we're covering this portion now because when we start talking about it in chapter 8, you would have already been equipped with the knowledge that you need. So slip typically occurs on the most densely packed planes, and it occurs in the directions with the greatest atomic packing. So the higher the planar density and the higher the linear density, the more or the higher the probability that you're going to get some slip. So again, this points to why this is relevant. So we're not just, I'm not just giving you formulas here, I'm actually giving you tools that you can use when you want to look at deformation of a particular material. So the final part of this chapter is on the application of X-ray diffraction. So this is how this particular tool or this particular instrument is one that is used to actually give or describe the crystal structure of a particular material. So if you've ever worked in a lab, or if you plan to work in a lab, X-ray diffraction is a very crucial tool for describing the solid structure of materials. And so you see this chart, which gives you the electromagnetic spectrum, right? So the very first class, we talked about how the electromagnetic spectrum is a stimulus for a particular property. I'll leave you to look back to your notes to figure out what that property is. But basically, with waves, we have this, waves exhibit this property known as diffraction. So diffraction occurs when a wave encounters a series of regularly spaced obstacles that are, one, that are capable of scattering the wave. So that means that basically the wave is not able to penetrate completely through. And two, these obstacles have spacings that are comparable to the wavelength of the wave. So to put it simply, the wavelength of that particular wave has to be equal to that dimension. So for instance, if I'm talking about radio waves and I want to diffract radio waves, that means the spaces I'm talking about have to be on the order of, thousands of kilometers, basically, or tens of thousands of kilometers for me to be able to figure out for me to be able to do diffraction of radio waves. Specifically in this particular section, we're going to be talking about X-rays. And why is that? Because X-rays are on this order of magnitude, which are 1 nanometer, and 1 nanometer happens to be 10 angstroms, and angstroms are a unit that are representative of atomic distance. So you can see that X-rays are right where we need to be if we're going to be describing crystal structures, because crystal structures are based on atoms and describing the planes between atoms. And so what happens? What happens when we do when X-rays are diffracted? So we start with one wave. So we have two waves here, wave 1 and wave 2, and wave 1, hits this atom and gets, diffracted in one direction. Remember that these are regular spacings, and because the wave cannot pass through this particular atom, it gets pushed out. And then wave 2 goes through and hits an atom below, and then gets diffracted as well. So we have these two waves coming in, which are your incident beams, and we have these two waves coming out, which are your diffracted beams. So something sends these waves, and then these two waves that come out are detected or read by something else. And so if you notice, wave 1 and wave 2 travel almost the same distance, except for this SQ and QT direction. So this particular difference here, right, this represents the extra distance that this wave traveled. And so this distance here determines what we call constructive or destructive interference. Basically, based on this extra distance, right, this extra distance helps us to determine whether these two waves are going to add up together, so that is they're constructive, or whether they're going to completely cancel each other out, so that's destructive. And so that whatever happens with this extra distance is what we base our detection on. And so there's a relationship between this angle, okay, and this angle is related to this extra distance. So if you look at this triangle PSQ, you notice that this angle theta has got to be related to SQ, right? The longer SQ is, the bigger this angle is, and so on and so forth. So there's a law known as Bragg's law, which relates the distance that these two planes A and B are separated by, and this angle here, which is related to the extra distance that the material travels. So in other words, based on what's going on here and based on whether we have constructive or destructive interference, we can find this interplanar spacing, and that interplanar spacing is related to this angle, okay? And so when we detect these beams, we'll end up with some graph that is a function of some intensity and some angle. And so what will happen is that this D, again, is related to this theta, and this theta is related to this extra distance. And through some mathematical and physical laws, we're able to calculate this interplanar spacing based on how these two beams convert. So in the next slide, you will see an example of what we'll call an X-ray diffraction pattern or an X-ray diffractogram, where you have these specific intensities which are related to certain angles. All right, so our diffraction angles, all right, so every time we have an intensity, we know that there's something interesting happening there. So at about 45 degrees, we're able to detect this 110 plane. At about 65 degrees, we're able to detect this 200 plane. At about 82 degrees, we're able to detect this 211 plane. So again, you guys are not necessarily going to be using X-ray diffraction in this particular class, but suffice to say that based on the principles of electromagnetic diffraction, based on the type of wave we're using, we're able to basically detect and define the crystal structure of a material. And so when we say that a crystal structure for iron, for instance, has a 111 plane, or we say, aluminum has a 100 plane, the reason for that is because we're actually able to detect that, okay? And so this concludes the lesson for today. Based on everything that we've discussed, you should be able to sketch a vector direction and a plane within a unit cell. You should be able to specify the Miller indices for a vector direction that has been drawn within a unit cell, and you should be able to calculate linear and planar atomic densities. Once again, the homework, the first homework is due tomorrow, Wednesday, September 13th. It is due at 5 o'clock. So please, if you've not started, because I know that some of you have not started and some of you are in the middle of it, make sure you start it and complete it by 5 o'clock. You only get one opportunity to do it. I hope you guys have enjoyed the lesson, and we will see each other on Thursday. Have a good week. Bye-bye.